About edge computing for structural health monitoring on resource-constrained devices. All right, so a bit of an outline on what I'm going to be talking about today. First, I'm going to go over an introduction and contributions that I've made, and then I'll also go over some of the publications I've had and presentations I've done on this work. And then after that, we'll talk about two main projects as part of this thesis. First one being joint deployable sensor packages, and then the second one being embedded sensing and electronics for structural health. After that, we'll just move on to conclusions and future directions for this work. All right, so as for an introduction, we would need to talk about what structural health monitoring is first. It's basically a method used to assess the condition of structures. Examples of things it would be used in are buildings, bridges, aircraft, ships, and electronics. And sort of a subset of that, a method within SHM to determine this stuff is the measuring and assessment of vibrations using accelerometers and FFTs for the frequency domain. This is a useful way of doing it because healthy structures oftentimes are relatively predictable because their frequencies won't generally change, but damage can alter those frequencies, and that is typically measurable. One issue that we have with traditional vibration-based structural health monitoring is that it relies on complex on-site tests and off-site data processing, which leads to latency and delays in decision-making for these types of problems. Our proposal for dealing with that is having edge computations made for preliminary examinations of these structures to increase safety and accelerate decision-making. And the main contributions of this work today are, first, the development of scalable frequency-based structural health monitoring frameworks that enable rapid damage detection using edge computing on resource-constrained devices. And then a couple more are the design and deployment of UAV-compatible edge computing sensor nodes and an experimental validation of onboard frequency-based damage detection. And then, like I said, there are a lot of publications on this work. Most of these that I've submitted are correlated with the stuff that we're going to be talking about today. And then we also have a journal paper in development about this stuff. And we also have a few more publications on here. As with the ones before, these mostly have to do with the same stuff of the work today. And this work has actually been presented a few times. It's been presented at the last 3 IMAX, International Modal Analysis Conferences. And then it's also been presented at SPI Defense and Commercial Sensing last year, and then an Air Force Research Laboratory Showcase last year as well. So for the first project, we're going to be talking about joint deployable sensor packages. And for that, we're going to be including information about a deployment and retrieval system, sensor hardware, an edge computing algorithm. And the idea with this is that it can be used after natural disasters to assess the safety of infrastructure before anything else. The idea with that is that you want to assess the safety of structures before any manned operations begin. So obviously, vibration-based SHM is just one facet of SHM. So you'd have something like this. You would deploy it out and get a preliminary examination of a structure to assess the safety. And if it seems fine, then you can continue with more manned operations. And then a lot of this is intended for use with bridges, as you can see here. So for the deployment and retrieval system, the sensor package, obviously, as the name implies, can be deployed from a drone. And this is accomplished using an electropermanent magnet, which receives a 5-volt pulse that changes the polarity of the magnet. And in this system, we actually use 2 of these magnets. We put one into a retrieval cone in the drone, and then we put one on the sensor package. So essentially, you have the magnet in the drone on here, but magnet here off. And then you just flip them to attach it to the structure, and then do the reverse to get it back. And then the idea with the retrieval cone is just that you're guiding the sensor package when you're retrieving it so that it lands safely on the drum. Onto the sensor hardware, the sensor package is made up of a few key parts. The first one being the 3D printed casing along with a 2-inch PVC pipe shell, as you can see here, casing and all that. That's essentially just to hold everything in place in the spot that we want it to. And then the next is the main printed circuit board here, which houses most of our electronic components. That would include the microcontroller that we use, as well as an SD card, a wireless transceiver for communication with other packages, and even power regulation, and also a real-time clock. And then lastly, the last key component is the daughter board, which holds the accelerometer on it here, and that would actually end up being right in this area of the sensor package here, right above where the EPM sits. And we have it right there so that it's connected on top of the EPM so that vibrations can propagate through the magnet to it. And then this whole sensor package is powered by a 2-cell 7.4 volt lithium polymer battery, which actually would just sit on the other side of where that PCB is in the 3D printed casing. And then you can kind of see how the different components interact with each other with this block diagram. The battery obviously powers the system. That goes through a power regulation that's on board the PCB. And then once the PCB is powered, a trigger can be sent to start a test. That can be done manually, digitally, or wirelessly, depending on which code we deploy to the system. After that, then the Teensy microcontroller basically handles all the other interactions. And that works with a pulse width modulation for attaching and detaching the magnet, and then working through the serial peripheral interface for all the other components like the accelerometer, the RF transceiver, the SD memory, and the RTC as well. As for how the sensor algorithm works, essentially the data that we're trying to look at, we want to process at the edge for rapid decision making. And for this, first, the sensor package is initialized as soon as it receives power. Then it records and reads data from the accelerometer. And we essentially right now are at a max of 16,384 samples. We needed that to be a power of 2 for the simplified FFT algorithm later on. And then we read at a rate of 1,600 samples per second. So once the data is read, then obviously we want to perform an FFT on the edge on it. And this is basically an early variant of the Cooley-Tukey algorithm, which is why it needs the power of 2, because it essentially just gets divided into even and odd indexed points and then combined later to become just one singular FFT. After the FFT is calculated, then the first modal frequency of the system is calculated after that, and that's with a basic threshold-based peak finding algorithm, which works on relatively simple systems. After all that's done, then the process is finished and the data is saved, including data on what the first modal frequency is. So obviously, we used a specific microcontroller for this. We used a Teensy 4.0, and we used that because it's useful for continuous structural health monitoring because of its large amount of memory for complex calculations. And then we also used the Arduino toolchain because of its simplicity and use with the Teensy. We wanted to figure out how the microcontroller performed with the algorithm, and we profiled it using GNU gprof. Essentially, we examined 3 main facets here. We looked at the time of each process, the cumulative time that gets added on from each process, and then the percent that one thing took of the total time of a test. So here, obviously, you can tell that data collection is the most time-consuming one, but that is only because we had a set amount of time for the test. We had 16,000 samples that we wanted to read, and then 1,600 samples a second, which gave us around 10 seconds. But for this, the times are relatively quick, and we ran 30 benchtop profiling runs for this, and all gave us pretty consistent results. And the numbers that you see here are actually just the means from those tests. Onto the actual structure testing, we wanted to create a controlled environment where we could measure the vibrational behavior of a square stock beam with pinned and roller supports. The goal of this was to assess the sensor's ability to measure across different structural conditions. To do this, we basically started with a single sensor package in the center of the beam here, as you can see, and then one roller support and one pin support equally spaced out from the center. And then we ran a test with that configuration. And once that was done, we subsequently moved the left side roller support incrementally for 2 more tests closer to the center, like this. For this testing, we use a modal impact tool to excite an impulse response in the system. Essentially, the sensor package would just continuously record vibration data from this. And one thing you can actually see here from that is how well the sensor package is able to see the differences in damping as each test goes. Obviously, you can see with each subsequent test, the impulse gets damped faster than the one before. Then after this was done, just like we said in the explanation of the algorithm, the data was subjected to FFT analysis with the primary focus of identifying first most frequency. So to verify the precision of the FFT that was computed on the edge, we computed another FFT off of the edge with a more complicated algorithm from NumPy to compare values. Visually, you can kind of see that the 2 algorithms match up pretty well. And then if you needed more verification, the root mean square errors of these respective tests are down here, and they're very low as well. Also, you can see that the system is reading changes in natural frequency successfully. These are actually the exact outputs from the sensor package, which match up pretty well with the peaks that you see here. To further verify the accuracy of the edge processed FFT, we compared it to the NumPy FFT with a frequency response calculation. In this case, you would want the response to be close to 1, especially around the modal frequencies, which would show a strong correlation between the 2 sets of data. And as you can see in the graph, the edge FFT is relatively close to the off-edge FFT, with the largest difference around the modes just being at this dip here, which was just 0.094 difference. Before we get into conclusions on that, we'll talk about the second project for this, which is embedded sensing in electronics. So the importance of this is that electronics can sometimes be in environments where they experiment high rate dynamic events. And the issue with that is that these impacts can actually damage electronics, causing them to not function properly. You might get something as drastic as, say, the top picture where something completely breaks, but probably more often than that, you get something like this bottom one where you have a component falling off. And our proposal to deal with this is that we want to use embedded sensors and later combine them with an edge processor to detect damage. And our objective here is to implement a frequency-based damage detection system in electronic assemblies. So before we get into what we actually did for that, we have to talk about what mechanical shock is. It's essentially a sudden change in force position, velocity, or acceleration, which can induce transient states of the system and excite system frequencies. And the issue here, obviously, is that that can lead to unpredictable responses within the structural integrity of components, leading to damage and everything. Some examples of mechanical shock would include stuff like blasts against civil structures here, car crashes, and even high-speed aircraft when they're accelerating very quickly. So the sensors that we wanted to consider for edge computing were an accelerometer and 2 strain gauges, one on the top and then one at the bottom use the top. We also connected a resistor with an extra mass, which was meant to be our component that falls off of the system. And the extra mass was actually added here just to exaggerate the difference in frequency that the component falling off would cause. We also included an accelerometer off to the side on the base plate here, which would give us our exact input signal to the system, and used high-speed cameras to visually capture the high rate tests. So like I said, we had a resistor with a mass on there. We essentially put that on there so that we could get an exact time reference of when it falls off. And we put it into a voltage divider circuit right here to be able to do that. Essentially, we fed it 5 volts from a power supply and then read from the first resistor so that we would get a continuous 2.5 volts when the resistor was intact. And then it dropped down to 0 volts when the resistor falls off. And then you can actually see an example of that here for a test when the resistor falls off. And you can see the rapid time scale that it happens to, happening just within that first cycle of the natural frequency of the board itself, just at that first peak there. So we also wanted to include finite element modeling for this study to see if the trend fits what we would expect from this. Obviously, that the decreased mass will increase the natural frequency of the whole structure. And then here are also the material properties that we used. So for these simulations, the resistor was added as a mass at the bottom of the board here that you can see at the top. And this produced the change that we were looking for, where the resistor being on it increased the mass of the board, therefore resulting in lower modal frequencies than the board without the mass here. And we're especially interested in this case in the first mode here because it results in the highest amount of displacement in that spot where the resistor is on the board, making it more likely to fall off. And also it's the easiest one to excite with these tests. Before I get into the actual experiment that we did, though, I'd also like to talk about the edge processing plan that we made for this. We didn't get the chance to actually implement it, but we did get the chance to get an idea of what we want. So just like with the sensor package, the approach would be microcontroller based, implementing an FFT computation on the data, as well as peak detection on frequency components. However, with this study, the idea is that we want to go further than that and possibly implement a vibration response and even maybe control later on down the road with something like piezoelectric actuators, which can dampen the vibrations. And part of our motivation here is that obviously this would reduce latency and decision making, make these electronics more autonomous, and prolong the lifespan of some of these PCBs and components. Some things that we figured we would need to consider, though, obviously, are first and foremost computational power. As we saw from the data in that resistor slide, this all happens on a very fast time scale. So your responses, if you are going to make them, need to happen on a very fast time scale as well. So you need something powerful enough to be able to keep up with that. The next thing, obviously, is sampling rates. You want to know the frequencies that your system is expected to experience. Microcontroller that can actually read stuff fast enough to keep up with that. And then lastly, you might have to consider algorithm optimization if your microcontroller is something that is a bit constrained on resources. Okay, so to get into the experimental approach that we did with this, to ensure a resistor detachment from the system, we used a drop tower to emulate high rate impacts at varying heights. You can see it in this video here, but in this video, we actually put it into a cantilever configuration so that you can see the vibrations easier in the video. But when we actually did testing, we put into a fixed configuration on it so that we would get that displacement at the center of the board where the resistor is. So we impacted it several times to get the resistor to fall off at varying heights. And you can kind of see what a before and after of that looks like here as well, with the resistor component stayed on there. And then this is what the paths look like once the resistor falls off. So these are high-speed videos. I don't know why they're not playing. This is a test, obviously, where the resistor stays attached. And then this other one here, which is a little bit more interesting, is when the resistor falls off. And you can actually see this didn't happen in every test where it detached, but the resistor just came back and impacted the board again, which acted as another impulse, making the vibrations last longer. Okay, so as for the experimental outcomes from this, we wanted to look at sequential tests leading up to a resistor detachment test to show differences in the acceleration that the system experiences when attached versus detached. So obviously you can see here that on a test where the resistor detached, the vibrations take much longer to dampen, and that's especially evident in the higher frequency components of this signal that you can see pretty clearly throughout the whole test, but are harder to see on the other tests. If you can count to 30, you can probably tell that we skipped test 29 here, but we had a good reason for that. Test 29 in this case, actually, the pad ripped out of the PCB, but somehow the resistor stayed intact. So we had the pad ripping out and the trace still continuous throughout the whole thing. And when we looked at the vibration data from this, we actually didn't see any significant change from these previous 3 tests and like the frequency or the time domain. Now, the issue with that is that while we didn't see it, we didn't know for sure that this would be considered fully healthy. So we didn't want to present that data as fully healthy just in case. So we decided to use those previous three tests, and we ran one more test to get the resistor to fall off, which worked, and that gave us the results that we were expecting in terms of vibration. So looking at the actual frequency domain, you can see that from those same tests, we see a trend that lines up relatively well from what we expected in the simulations here. For the test where the resistor stays attached, the first modal frequency is around 258 hertz tested, which is just an 18 hertz difference from the simulated one. And then for the one where it detached, the tested is 354 hertz, which is a 30 hertz difference from simulated, but both relatively close and gave us the trend we were expecting. Okay, so on to the conclusions and future directions from both of these projects. First, we have that edge computing and embedded sensors work well for rapid damage detection. Onboard FFT computations closely match offline high precision results, and systems like these can operate in the field. And then lastly, this approach enables early warning mechanisms for structural health and dynamic shock environments. And as for the future directions, for the sensor package, this will include improvements to the algorithm, including investigating different peak finding algorithms, stuff that could be like more complicated and work better in noisier settings. And then also a way station is in development, which could communicate with multiple sensor packages for offsite data reading once the data is already processed at the sensor. As for the electronic assemblies, future work will include implementing edge processing with a microcontroller, obviously, like we talked about in that part of the project, but then also vibration response capabilities, which we also mentioned using piezoelectric actuators. And you can see here on the right a preliminary look at what that might look like with these circles here being piezoelectric actuators that we found would be best placed around fixities where the strain is highest. And then lastly, for this, we would probably also look at controlled failure methods for this. Obviously, we just soldered a component on there and tried to get it to fall off. But if you wanted to control this even more, you could look at the exact amount of solder that you were putting to attach each component. And then you could also change the orientation of the component and change the orientation of the PCB and different things like that. And then lastly, I'd like to acknowledge the AFRL, the AFOSR, and the NSF for partially funding this work. And that's it.